So, let's now look at our example of applying the Heisenberg uncertainty principle to estimate the size and energy of the hydrogen atom. So, of course, we need the basic ingredients to our problem. So the basic ingredients that we have, of course, is that we're going to bring together, much as we had discussed at the beginning of the semester, we're going to bring together our two constituents, namely a proton, which is positive, and an electron over here. And the electron will have, of course, its charge, which is minus the fundamental charge E, and it has its mass, which I will denote lowercase m. The proton, on the other hand, will have a charge capital Q, which is positive, and it's just positive value of the fundamental charge. And it, of course, has a mass which is much larger than the electron mass. You may recall from earlier in the semester for the proton or the hydrogen nucleus, that mass is about 1,800 times more than the electron mass. And finally, in addition to these two basic constituents that we're bringing together, we have the interaction between them. There's a potential V of R. And that potential, as you know, right, is the third ingredient, right? It's the Coulomb potential. It's Empedocles' attraction and repulsion, love and strife. So that potential V of R then takes the form of Coulomb's constant times the product of the charges. There's a plus E and a minus E from the electron, and then divided by the distance between the two particles, r. So this will be my separation r. And we can simplify this. There's a net minus sign, so it's minus this combination of constants, Coulomb's constant, E squared. And that's a combination we will see come up quite frequently, times then 1 over the distance. Now, before we begin in earnest on the analysis here, I want to point out one other thing. You all presumably have some experience with these types of orbital mechanics problems. You know that what actually happens is that both of these particles actually independently orbit around the center of mass of the system. But because the proton is so much more massive, right, the center of mass is essentially, it's 1,800 times closer to the proton. So it's essentially located right at the location of the proton. So the proton, for all intents and purposes, is basically stationary. It's very much like orbital problems where you deal with the sun, right? You can pretty much ignore the motion of it compared to the motion of the planets. So it's basically stationary. The error we make here by ignoring this is about 1 part in 1,000, which is much smaller than the type of order of magnitude errors we're going to be making because we're just using a simple Heisenberg analysis. So regarding that as stationary, here's how we would begin to think about the problem. The first thing you want to consider in any quantum mechanical problem is a proper starting point. And now in standard mechanics, or in your first mechanics course, what you learn to do when you're stuck and you don't know where to begin is just to write down F equals ma. Later on in classical mechanics, you learn something a little more sophisticated. What you learn is the first thing you need to write down is the Hamiltonian of the system. Because once you have that Hamiltonian, you can then get all the equations of motion and to solve for the behavior of the system. And in quantum mechanics, it's the same thing. The first step is always to write down the Hamiltonian of the system. So that's just, we're going to write down the Hamiltonian. And we know what the Hamiltonian is, right? It's just the total energy of the system, where we write the total energy in terms of the momentum. Now, the total energy is, of course, kinetic plus potential. The kinetic energy in this case, as we've said, we can treat the proton as basically stationary, so we only have the momentum of the electron to worry about. That's going to be p squared over 2m. That's how we write kinetic energy in terms of momentum. And the potential energy in the system we have defined for ourselves here. It's minus Coulomb's constant times E squared times 1 divided by the separation between the two particles. The second step then is we can then begin our quantum mechanical analysis by thinking about how the various functions behave in terms of their location, and also in terms of momentum. So first, let's consider how the various functions that are critical to us behave as a function of distance between the particles. Now, the first critical function here, of course, is the potential. So let me sketch the potential. I want you to notice that this potential energy is negative and it diverges as r goes near the origin. So it's going to go down towards infinity here. But then as r goes towards 0, it begins to approach the horizontal axis from below, like so. And so this is a graph of my potential V of r. And of course, there's a corresponding curve on the other side of the proton, right? So the proton is basically sitting down here at the origin. Now, if we were to carry out a classical analysis and ask, okay, what will happen to this system eventually, there's a very important principle that helps us carry out the analysis. And let's mention this principle that we're going to use. The principle is that after a long time, systems tend to settle down. Systems tend to settle to their minimum possible energy state, if you want to call it that way, the state in which they have minimum possible energy, right? So you guys may be familiar with, and that's just a general principle of physics, right? If we have a system, when we first build it, it might be in some excited state, right, that has some extra energy to it. But over time, one way or another, by hook or by crook, the system is going to tend to lose energy to its environment until it gets to the point where it can no longer lose any energy when it's reached its actual minimum possible energy configuration. A classic example of that is, in fact, the classical electron orbiting in a classical orbit around the proton. What happens, of course, is that as it's orbiting, it tends to emit radiation and thereby lose energy, and so that orbit eventually spirals into the center. From another way of looking at this, then, if we look at placing a classical particle on this potential energy surface, we know, of course, it will eventually then try to find the minimum possible energy, which is just to go and sit perfectly exactly on the nucleus here at the origin. Now, there is, of course, a difficulty with that, which is that, well, if we were to do that, you notice that the electron then would be very highly localized near the nucleus. So you'd have this very sharp peak here. Now, notice, I'm not drawing it infinitely sharp, because we already know infinitely sharp is not very likely to happen. And that's because of localization energy. There's this rather large energy cost to localizing a particle that goes like 1 over the distance to which we've localized it squared. Right? So if we actually have this perfectly localized on the origin, it would have an infinite amount of localization energy. So that's not what's going to happen. It's going to take on some kind of a spread here around the origin. And whatever that spread is, we will call it delta R in our kind of order of magnitude Heisenberg analysis sort of a way. And our job is basically to find out what delta R wants to do. Certainly the potential would like to see delta R shrink to 0, but there's a countermanding effect. So this graph is actually the probability as a function of R. So I'm putting actually 2 different functions here on the same graph. So you can sort of compare what they are doing. Probability builds up, of course, where the potential is the lowest because we're trying to minimize the energy of our system. Now, the next thing to consider is what's happening with momentum. So if we do momentum measurements, right, we will get a spread in general. Now, I don't expect on average there to be any average momentum, so I'm expecting a peak that looks something like this, centered at 0 momentum, but this peak will have to have some kind of a width associated with it, and that width we will call delta P. And of course, from Heisenberg uncertainty, the least that P can be, we know it will always be at least as big as h bar over 2 delta R. And we certainly want it to obtain its least possible value if we're trying to minimize the energy of our system. Now, uh, our task now becomes trying to estimate the least possible energy that we could obtain on average. So the average energy of our system, which we eventually are going to try to minimize, right, is actually equal to the average of the sum of these two terms, which represent the energy, right? The Hamiltonian, numerically speaking, is equal to the energy. And we know, even if our variables are highly correlated, the average of a sum is always the sum of the averages. So I have to write down the sum of the average of these two terms. So there's p squared over 2m. That's the kinetic energy term. And then there's minus Coulomb's constant times E squared times the average of 1 over R, where I've used the fact that the average of a constant times a variable is just the constant times the average of the variable. Now let's begin to think about these terms separately. This first term is nothing other than the localization energy, right? We've already handled this before. We've already reasoned the size of this quantity, right? We know we want to make the least possible spread in the momentum, so we will set a delta P equal to h bar over 2 delta R. We can substitute this term in here then essentially for the average of for P, right, and then square it. And this is just confinement energy. And we already have a nice expression for that, so I'm not going to repeat that argument. But the confinement energy is h bar squared over twice the mass times the square of the size of the region to which we've confined things. So that's h bar squared over twice the mass of the electron times the size of the confinement region, which is this delta R, quantity squared, like so. Now, I want to emphasize again, right now we're just doing order of magnitude estimates, right? I'm quite aware that we're drawing one-dimensional pictures here, and there's really things going on in all three dimensions in an atom. But again, this is just order of magnitude type analysis. We could even put a little approximately equal to remind us of that. Now, that helps me with the kinetic energy, which gives me this confinement energy. For this term, I have to think a little harder, right? I'm looking at the average of 1 over delta R, so I can bring out 1 over R, Coulomb's constant E squared. Now, when I average this quantity, order of magnitude-wise, it helps to think about what sizes of R are most commonly going to come in. Now, when I have a distribution like so, right, whatever its width is, it's very unlikely, we've talked about this before, it's statistically extremely unlikely I will ever hit exactly R equals 0. Which, by the way, is a good thing because 1 over 0 would be infinite, right? So I don't actually have many very small distances that I'm averaging together. Likewise, it's unlikely that R is going to be many times this width, many times this delta R, because the probability of being out there is just so low. So statistically speaking, the most typical values that I get for R are the ones that correspond to this typical width. So the numbers that I'm averaging are typically 1 over my typical value of R. So I'm averaging together a bunch of terms that all have the same basic size, namely 1 over delta R. So order of magnitude wise, right, very approximately order of magnitude, I can simply say that, well, the average of 1 over R is about equal to 1 over delta R. It's statistically not really true. It depends in detail on the shape of the distribution, but generally speaking, that shape will just put in a factor of 2 or 3 or something along those lines. Very good. So this is now our estimate. And our job then is to try to figure out for my system, this is its energy on average. My job now is to try to figure out how much width I can expect here. And that happens by trying to minimize this energy. Now, if we think about this function, we can learn some interesting facts about it. The first thing I'd like you to notice is that here, if I plot my average energy as a function of delta R, The first thing I'd like you to notice is that when delta R is relatively large, 1 over delta R squared will be much smaller. I will be dominated by this term, which is coming from the potential. So as long as I don't localize things too much, I get a term that is negative, and it approaches 0 from below. So it's going to look something like this. And this term is doing exactly what the potential would want us to do. It's saying to minimize my energy, I want to make delta R as small as possible. But when delta R gets very small, near 0, in that case, this term becomes much larger than the second term. So I'm dominated by this positive term, which actually diverges up towards positive infinity. And what this term comes from is my confinement energy. So what it's saying is eventually, if I make delta R too small, I've confined my particle so much that it has such a wide spread in momentum that on average I've got this huge kinetic energy cost. Finally, because this is a nice continuous function, we know we have to connect this up in a continuous way. We see then that our function has to have some kind of minimum value. And that minimum value, I will call delta R star, that then represents the minimum energy configuration of my system, and that then is what's going to tell me exactly the size of my atom, delta R, the spread that the electron should have. So now we're going to go ahead and to determine that through, kind of standard calculus approach by setting our derivatives equal to 0.